In this set of videos, I want to talk about the chain rule as a technique of finding derivatives, especially for derivatives involving function composition. So in this list here, we have some comparison functions. On the left, we have functions that we can find the derivative of easily without the chain rule. For example, if I label these 1 through 4 on the left side there, then I can find the derivatives easily. The derivative of y equals x squared plus 1 is simply 2x. The derivative of sine x is cosine of x. The derivative of 3x plus 2 is just 3. And the derivative of x plus tangent of x is 1 plus secant square of x. So we know how to do those. However, the column on the right, if I label those 5 through 8, these are not as simple. We have function composition. We have square root of x squared plus 1, or sine of 6x, or 3x plus 2 raised to the 5th power, or x plus tangent of quantity x squared. And we're going to deal with these in much the same way that we worked with the simpler forms of functions, except with one twist at the end. And in order to be successful at using the chain rule, we have to be able to distinguish between the outside function and the inside function. So let's just say we have some function f of x, and we have another function g of x. Then we could compose those two functions together into h of x is equal to f of g of x. And so the function g of x becomes the input to the function f of x. Now, obviously, when we're taking the derivative of this h of x, we have to take into account not only the f function, but also how the g function is changing as well. And it turns out to be this simple. The derivative of h of x, when h is defined as f of g of x. I'm just going to move these functions around for a bit. The derivative h prime of x is the derivative of the f function evaluated at the g function times the derivative of the g function. And this is what we call the chain rule. So for example, with example 5, if we first rewrote square root of x squared plus 1 as x squared plus 1 to the 1/2, we would say that y prime is equal to the derivative of the outside function, which is something raised to the 1/2 power. And the way we find the derivative of that is we bring down the half and we reduce the power from 1/2 to negative 1/2. But we're going to leave the inside alone. Now that might be the way you would intuitively go about finding this derivative, but there's one extra step you have to add on to that. You have to multiply this by the derivative of that inside function, x squared plus 1, which is 2x. And if you were to rewrite this, you'd get 2x in the numerator and 2 times the square root of x squared plus 1 in the denominator. Then those 2's will cancel, and you end up with x over the square root of x squared plus 1, and that is the derivative of the square root of x squared plus 1. With number 6, we have the sine of 6x, and so we take the derivative of that outside function, which is sine, and that becomes cosine. We leave the inside part alone, and then we multiply by the derivative of the inside, which is 6. And simplifying, we get 6 cosine of 6x. With number 7, again, we have 3x plus 2 quantity raised to the 5th power. So our outside function is something to the 5th power, and the inside function is 3x plus 2. How do we find the derivative of something to the 5th power? We bring down the 5. We reduce the exponent by 1. We leave the inside part alone. And then we simply multiply by the derivative of the 3x plus 2, the inside function, and that's 3. A little simplifying, we get 15 times the quantity 3x plus 2 raised to the 4th power. Now we don't want to multiply this out because we want to find out where this is going to equal 0. And we can see right away that that derivative will be 0 when x is equal to negative 2/3. Finally, for number 8, we have x plus tangent of quantity x squared, and the derivative of x is 1. Now the derivative of tangent is secant squared. We're going to leave the inside alone, and we're only using the chain rule on the tangent of quantity x squared. So we're only going to multiply that by the derivative of x squared, which is 2x. And we end up with 1 plus 2x secant square of quantity x squared, and that'll do it for this.